Bucero, and her topic is global polynomial optimization with moment matrices and border bases.
Okay, good morning, and thank you for giving me the opportunity to participate in this workshop. Our problem is find the infimum of the real polynomial function on the semi-algebraic set S defined for the equality G and inequality H non-negative. Our objective is so the ERC of the realization problem is set. Find two criterion to detect when this optimum is researched and when eventually this criterion is satisfied. And finally, when this criterion is satisfied, recover all of the points where this optimum is researched. So there are a lot of words about this same subject. For example, the first word that solved this minimization problem as a ERC of the realization problem involving the semi-definite moment problem is the word of Lazare in 2001. After this word, there are a lot of words. For example, in the topic of the finite convergence, there are, I list some of them, but in this word, prove that the inertial realization problem is set under some fine radical or regularity condition. For example, for the topic of the final certificate for the convergence, there are the work on me 2012 about the flat truncation. And for the topic of the how to recover the minimized ideal, there are the work of Lazare, Laurent, Morin, and Trebuchet about the how to compute the real radical of an ideal. So if we can take the Lagrange multiplier, we can obtain an equivalent problem of the first problem. Is this problem that we find the infimum of the polynomial function f with the constraint of the gradient on capital F is equal to 0. And capital F we define it like this, and we can define the gradient ideal like this and the gradient variety like this. So if we can eliminate the variable s, we can obtain this equivalent problem. That is the problem with Kuhn-Tucker, and this we can define the Kuhn-Tucker point with like a point with there is an U1, UN1, and B1, BN2, such that we have this relation. We can define S Karas-Kuhn-Tucker, the set of the Karas-Kuhn-Tucker point of S, and we can define also the Karas-Kuhn-Tucker minimization of F on S. Point of Kuhn-Tucker such that this point minimizes our function. We can also define the Karas-Kuhn-Tucker ideal and the variety of the Karas-Kuhn-Tucker variety. So we can define the minimizer variety like a real point who vanishes vanishes in the gradient of capital F and minimize the function f, and we can define also the minimizer ideal. We have a proposition, a consequence of this ideal and gradient. So if we can take the projection in Y of the real gradient variety, we obtain the real Kuhn-Tucker variety intersect with the points that do positive the H. And we have also, if we project the gradient ideal over Y, we obtain the Kuhn-Tucker ideal. So our contribution are when the optimum research in Kuhn-Tucker minimizer of S, we obtain that the ERT of the realization problem is exact. Also, its projection. We obtain also when this minimum is at a research, we obtain the minimizer ideal. And one of the other results is we have a new representation of positive polynomial on S. And if the minimizer variety is finite, we can obtain a new criterion to detect when we obtain the minimum and satisfy certificate for a high degree. We have also a new algorithm for compute the minimizer ideal, and we reduce the size of the SDP problem using the border basis. So now I am going to define our hierarchy of the moment problem. We can take a finite subset G and H in Ry, and we define the preordering module H like this. This is the definition usual. We define the dual con PEGIH with as the polynomial in the sum of the polynomial in this set and in the preorder. We define the primal con like LEGH is the linear form semi-definite positive. We can define F mu EG as the infimum of the lambda F with lambda in LEG as and lambda 1 equal to 1. And we define also F sum of square EGH with the maximum of the gamma such that F minus gamma belong to the dual con. And we define F star, the infimum of the F, or the infimum of our function in the point of the H cacat. So for a degree T, we can take the prolongation of J in degree T, and we obtain this relation with the degree growing, the primal and the dual problem. And also, we obtain this property with the minimizer variety is not bit, and when the real variety of G intersect with the as positive, is including is included than the minimizer variety. We have this sequence, this growing sequence of this different extremum. We have also the realization. So now I'm going to give a definition. We define the Hankel operator associated to the linear form. The application dE to dual E such that for all polynomial P we have P by lambda. We define the kernel of this truncated Hankel. The polynomial in E such that the p by lambda is equal to 0, and if we can take this Hankel matrix with the monomial basis and the dual basis, we take the moment matrix defined like this, and we can define also the linear form generic for F is the linear form that the rank of this moment matrix is the maximum of the rank of the moment matrix associated to the linear form belong to LEGS, and lambda F is equal to F mu. And how to find this generic this linear for generic for F? We solve the SDP problem, and for this subject I use the tool like SDP or CSDP or CDUMI. So now I give the main result. If F is non-negative on SKGT, we can decompose F in a sum of the preordained module module of S plus a radical of the projection of the gradient ideal. And if F is strictly positive in SKKT, we can decompose F in the preordained plus projection in X of the gradient ideal. So if we compare this result with the result of Demelny and Power in 2007, we can see that in the result you use all of the variables in the Karlsruhe ideal, and we only use in X, so in X, sorry. And another consequence of our theorem is the corollary of Niedemel and Stomfer. This is the minimization without constraint, and we will use the gradient ideal. So another main result is we can take an G in Rx. We can take the hypothesis in G and the minimizer variety, like the real variety G intersection with the S positive is between the minimizer variety in X and the projection in X of the real variety of Karlsruhe, and the minimizer variety is not big. MP, sorry. 6 degree, such that we can take a degree equal or bigger like this and take the lambda generic for L. We get finite convergence. If we take the kernel or this moment matrix in this degree T, we can obtain the generator of the minimizer ideal in X, and if we have that the variety of G in the complex is contained in the projection in X of the variety of the Kuhn-Tucker, we have that there is no duality gap. We have this similar theorem in Ry with this condition. For the certificates of the convergence, we have this new theorem that we have take a monomial basis B, we can take E also in Rx. We have that F belongs to the linear span of E by E. B plus is contained in E, and GB is contained in the linear span of GE, and H by B is contained also in this same linear span. And we have also the hypothesis in G on minimal variety plus the minimal variety is finite. And we take the lambda generic for F. And plus we have the flat extension condition. We obtain that the finite convergence and there is no duality gap, and we can recover all of the point of the minimized ideal with the element of the kernel of the moment matrix. And we can prove also that if we have the G and H in Rs and the hypothesis of G and minimized variety plus the minimal variety is finite, we can obtain, there exists a degree such that for all degree equal or bigger than this degree, for the lambda generic for F, we can obtain a vector space E and monomial basis B with the condition A1, 1, 2, 3 of the above theorem. So the consequence of these theorems are that we obtain a generic case of the work of Ni in 2001. That we can take this matrix and we can take the variety of this delta, that is the point in the complex with the rank of the matrix A is less or equal to N1 plus G, the cardinal of G. And we can take G like all of the equation G and the JI, definitely like this. The conclusion is we can take this set is regular. That means that the different gradient is linearly independent when the S is equal to 0. Plus, we know that if reserved is minimum, then we have the finite converse and minimizer ideal theorem. And the same case, we take a regular set. We obtain the generalization of the work of Hub and Pan in 2010. And we obtain also the same conclusion. But I need that for the duality gap, I need that this set is irregular. And now I am going to talk about my algorithm. We suppose that the minimizer variety is finite. We take we have a polynomial function. We take G with this condition. First of all, we take the degree T, 1/2 at the maximum of the degree F, G, and H. We compute the generic, the lambda generic for F, solving the HDP. We can check the certificate. And if this certificate is okay, we compute the generator of the kernel of the moment matrix, and we obtain the minimum also. We have combined this algorithm with the border basis in order to reduce the size of the moment matrix. For example, I'm going to give two examples. Everybody knows the Robinson polynomial. It's a polynomial positive, but no sum of square. Okay, I try to minimize this polynomial. In this technique, it's not. I try to fix the minimum And when the minimum is fixed, we try to look the rank of the matrix, and like this we obtain the minimum. So we take the degree 3. The size of the moment matrix is this size 10, and the minimum is minus 0.93. We take with degree 4, and the size is 15, and the minimum is 0. That this is the good minimum. So I try to look in degree 5. The minimum is 0. So we compare. We prove that is the same minimum. So we look the rank of this matrix, and we obtain that is 8. So we calculate the border basis, and we obtain that the kernel of this border basis is not 0. So it's not the good kernel. So we try with degree superior degree, and we obtain the good result, the 8 point. We can also the sample with constraints. We take a degree 1, and we obtain the minimum minus 36. In degree 2, we obtain the minimum and minimum different minimum, and with degree 3, we see that is the same. So we take we look at the rank, and we take the generator of the kernel, and we obtain the good minimum. So this algorithm is implemented in the package border basis in mathematics. For solving the SDP, we use the SDPA and CSDP. We can compare our algorithm with the algorithm of Glossy-Poly, and we see that the size of the moment matrix is small. For example, in Moskin, the size is 55, and in our method is 19. We can compare the other. And the future work is application in tensor decomposition. What's happening is the minimized ideal is not 0-dimensional. What's happening when the minimum is not researched, and how to solve the numerical problem in the SDPA. Thank you.
Questions?
So how do you find the border basis? I guess you need to reduce eliminate the function multipliers and the new variables. So you do that, how should you do that?
Yes, for example.
So for general problem, how do you generate a basis B? Border basis.
Yeah. So the border basis is the basis like we can decompose like this. This is the border basis for the basis B. So each polynomial in R is we can reduce in element of only in element of B. It's like this for the reduction is we can reduce.
But how do you get the basis? You use
an algorithm.
You use for example graph basis. I guess the computation of the basis may be harder than to solve the problem. Yeah. So that is my concern.
The question is how I compute the border basis with another algorithm. who compute the border basis also.
The question is, I mean, if you compute the border basis, it can also be time to consuming.
Yeah, yes, yeah. It might be harder than the solve the question.
So,
Yeah.
what is your smart algorithm?
Okay, no, but the time for the calculus of the border basis is not it's not hard.
It's not hard.
Yeah.
Why? I mean,
Not hard, okay.
Yes, no take a lot of time for compute.
Compared to the SDP solving part, it's much less.
okay. Other questions? Well, then let's thank the speaker again.